Okay, so this evening we are going to look at how to work out the resultant force, which is what we need for us to find the acceleration of something. What the acceleration is going to be if we have an object of mass m. So in our case, the first thing we're going to do is identify which forces we're interested in. So the first situation you're looking at is the motion of a box on a flat horizontal surface. This motion of a box on a flat horizontal surface is what we actually have in this diagram here, figure 1. So with this situation here, we need to find out how much the resultant is going to be. So there are two directions in which this particular box could move. Either it could move in the horizontal direction here, which is the x direction or the x-axis, or it can move along the y direction, which is the y-axis. In our case, since the box is moving on a flat horizontal surface, we see that the box actually does not move in the y direction. It does not gain any height, or it does not lose any height along the y direction. Since the box doesn't gain any height or doesn't lose any height along the y direction, the acceleration of this box along the y direction is equal to 0. So the y component of the acceleration along the y direction or in the vertical direction is equal to 0. We choose the direction which is pointing up, the direction above the surface, to be the positive y direction, and the direction below the surface to be the negative y direction. So any force which is pointing above the whole surface or in the positive y direction, that will be treated as a positive force, and the other force which is pointing in the negative y direction, which is the weight of the box here, Fw, that is what is going to be treated as a negative force. So we have the normal force, which is the reaction of the box to the weight. That is what we are taking as a positive force. Then we are choosing the weight which is pointing down in the negative y direction to be a negative force. So these are the only two forces we can identify along the y direction, unless there is another force which I'm not seeing, but these are the only two forces we can identify as acting along the y direction. So we add these forces. The normal force is positive because it's pointing in the positive y direction. The weight of the box Fw is negative because it's pointing in the negative y direction. So when you add these forces, this is what we end up with as a resultant force. The resultant force along the y direction is going to be the normal force, which is positive. It's pointing in the positive y direction, plus Fn, then plus the weight of the box, which is pointing in the negative y direction. So this is a negative force, like this. So when you do this addition, what we see is that our resultant force, Fy, is equals to Fn minus Fw. This is the resultant force. This is how you get resultant forces. You identify forces, then you add them. Since these forces are vectors, in our case, we are using the xy plane. Any force pointing in the positive y, we treat that as a positive force. Any force pointing in the negative y, we treat that as a negative force. If a force is pointing in the positive x, we treat that as a positive force. If a force is pointing in the negative x, we treat that as a negative force. That's all we do. So we have found the resultant force to be Fn minus Fw. Now, along the y direction, like I've said, this box does not move along the y direction. It doesn't gain any height. It does not lose any height. The velocity of the box along the y direction is the same. So we write Newton's second law of motion to be this. The resultant force in the y direction equals to the mass multiplied by the acceleration in the y direction, where this m is the mass of the box, then ay is the acceleration in the y direction. And when we have this, we have an expression for the resultant force along the y direction, which is this, which is Fn minus Fw. Okay, then we, just a minute. Then we substitute for our expression for resultant force here, so we end up with Fn minus Fw equals to ma, which is what we have in equation 15 here. Now, there is no acceleration along the y direction. So the acceleration along the y direction is not there because this box does not leave the surface on which it's on. It's just on that particular surface. So in that case, our acceleration in the y direction, ay, is equals to 0 meters per second squared. So we substitute this value of acceleration there, so you end up with Fn minus Fw is equals to the mass multiplied by the acceleration, which is 0. This 0 acceleration multiplied by mass gives you a value of 0. So you end up with Fn minus Fw equals to 0, and that's how we come to the conclusion that the normal force, Fn, is equals to the weight, always. The normal force Fn is equals to the weight of the box. So that is the conclusion which we draw from this, the movement of the box along the vertical direction. There is no movement of the box along the vertical direction. So in this case, this is a conclusion which we draw, that the normal force Fn is going to be equal to the weight of the box. Are we clear? Is it clear on how we have come to this conclusion that the normal force is equal to the weight of the box?
Yes, sir, it's clear.
Okay, next we move on to what's happening along the horizontal or along the x-axis. So along the x-axis, there are two forces you can identify from the box. There is this force F, which is the force making the box move in this particular direction. There is also the friction force FF here. The friction force opposes the motion of the box in that particular direction. So this force which is pointing in the positive x direction, we choose this to be a positive force. The friction force which is pointing in the negative x direction, we choose that to be a negative force. So we use these two forces, this F and the friction force, we use these two forces to work out the resultant force along the x direction. So in that case, when you do that, this is what we get. So the resultant force, Fx, along the x direction is going to be equals to the force which is pulling the box or pushing the box towards the positive x-axis plus the friction force. The friction force is pointing in the negative x direction. Okay, so it's opposing the motion, so it's a negative, it becomes a negative FF. So in this case, we're going to end up with the resultant force Fx being equals to the force which is pushing or pulling the box minus the friction force. So this is the resultant force along the x-axis. Remember, a resultant force can end up being 0, like in this case, where we have here Fn minus Fw here. In this case, our resultant force ended up being 0. So this resultant force, if the resultant force is equal to 0, then you do not get any acceleration, which means that the velocity of the box does not change. If the velocity of the box does not change, then yeah, that's something which you can predict. You know where to find the box since its velocity is not changing. So in this case, we have our resultant force along the x direction as being equals to F minus FF, like that. So with this expression of resultant force, we use Newton's second law of motion in equation 18. In equation 18 here, so we, on the left hand side, you have the expression of resultant force. Then on the right hand side, you have the mass of the box and the acceleration along the x direction. So if there are a number of situations which can happen. The first situation is that the box does not move. If the box does not move, that means the box remains motionless. Or if the box moves at constant velocity. Under these two circumstances, if the box does not move, or if the box moves under constant velocity, then the acceleration is equals to 0. So if the box remains motionless or remains at rest, or the box moves, but it's moving with a constant velocity, under these two situations, then the acceleration along the x direction is going to be equal to 0. There are also other situations which can happen where the box can move faster and faster, that meaning that the velocity of the box is increasing, or the box can slow down, meaning that the velocity of the box is reducing. If the box moves faster, the velocity changes. If the box slows down, the velocity also changes. So under these circumstances, then there's going to be a value of acceleration. So the first situation we're going to look at is when the box decides to remain motionless. So it doesn't move along the x direction. It just sits there. So in that case, the resultant force is the same. Whether the box moves or doesn't move, how we get the resultant force is still the same. It's the F minus FF. So in this case, if the acceleration is equals to 0, the box is motionless, then we substitute for AX here, put there, then you end up having F minus FF equals to 0, M, the mass, then multiplied by the acceleration, which is equals to 0. The mass multiplied by the acceleration of 0 gives you 0. So you end up having F minus FF is equals to 0. And that gives you the force with which you are pulling the box to be equal to the friction force. This friction force, since the box is motionless, this friction force, since the box is motionless, is what we call the static friction force, because the box is not moving. That's what you call static friction force. So the F is the pulling force acting on the box, the pulling force acting on the box, then the FF is the static friction force which is acting on the box. Excuse me. Yeah, this guy is trying to teach also. Okay. So the friction force, as we have seen from last evening, the static friction force, the friction which is exerted on an object when it's motionless, is equals to the coefficient of static friction multiplied by the normal force. Okay. However, we have seen that the normal force here is equals to the weight of the box. Therefore, what we end up having here is that the normal force equals to the weight of the box equals to weight is mass of the object multiplied by G. So our friction force, our pulling force actually, since a pulling force is equal to the friction, the static friction force becomes equals to F, becomes equals to the coefficient of friction multiplied by the mass multiplied by G. So you can actually predict how much force you need is required to make sure that this thing, how much maximum force you need to apply until just this thing is about to start moving. So it's not yet moving, but what is the maximum force you can apply until such a point that this thing is just about to start moving, which is this force here. The other case, is it clear on what happens when the box decides not to move and what you have done? It's clear?
Yes, sir.
Okay. The other situation you can have is if the box decides to move, but it moves with constant velocity. Okay? In the case where the box is not moving, the position of the box does not change. So the box is in a particular position, it doesn't change. The velocity of the box also doesn't change. However, if the box decides to move with constant velocity, the position of the box will change. Where the box is going to be after a certain amount of time, it's going to change. The thing which is not going to change is the velocity. We are saying that the box is going to move with constant velocity. Since the velocity is constant, then it also means that the acceleration along this direction, AX, is going to be 0 meters per second. We already have an expression of resultant force, Fx, the sum of Fx, but now we also know that if our box is moving at constant velocity, the acceleration is going to be equal to 0. So when we substitute for the value of acceleration here, we end up having, and we also substitute for the resultant force, which is along the x direction, which is F minus the friction force equals to the mass of the box multiplied by the acceleration. So when you do this, the mass multiplied by the acceleration, that gives us a 0. So we end up having F minus FF, which is equals to 0. We end up having F equals to the friction force, this. However, because this equation here, F minus F equals to FF, this equation 24 looks exactly like equation 19. But in these two equations, the equation number 19 and equation number 24, the friction is different. In equation 19, the box is not moving. So the friction is what is called static friction force. And we have seen how to get the static friction force. It is a coefficient of static friction multiplied by the normal force. In this case, F is equal to F again. This friction is no longer static because the box is moving. So if the box is in motion, then the friction which the box experiences is what is referred to as kinetic friction force. And how do we get the kinetic friction force? The kinetic friction force is equal to the coefficient of kinetic friction, mu k, multiplied by the normal force. And we recall that our normal force is equal to the weight, which is equal to mg. So our friction force, Fn, if we substitute here, our pulling force in this case is going to be equal to mu k multiplied by mg. So you can see the force with which the force in equation 27, it's mu k multiplied by mg. Then in equation 22, the force is mu s multiplied by mg. However, mu s is always greater than mu k. Mu s is always greater than mu k. So when you're pushing or pulling something which is already moving, you actually apply less force because of that coefficient mu k, which is less than mu s. However, for you to push or pull something which is stationary, you need to apply a larger force than you would apply when that particular object is moving. The reason why that is the case is because of this guy, mu k. Mu k is always less when the object is in motion. Okay, any question? Any question? Is it clear?
Yeah, is there a difference between static friction and the one that you just spoke about?
Yes, there's a difference. Static friction is the friction which an object has when it's not moving. And kinetic friction is the friction which an object has when it's moving. Usually, static friction is greater than kinetic friction. The reason why it's greater is because the coefficient of static friction is greater than the coefficient of kinetic friction. This mu k. This is for kinetic friction. It's less than. This is less than this mu s. Mu s is typically around 0.8, but mu k is typically around 0.1, 0.2. So yeah, there is a difference between static. Static is the friction which a body has when it is at rest. So it doesn't mean that when something is not moving, there is no friction. No, friction is there. Any other question? Sorry? Is it possible that there's what? How can it have friction when it's not moving? Friction depends on where you are. It depends on what kind of flow you have, and it also depends on the mass of that particular object, right? So friction depends on mass. It depends on the weight of the object. So as long as an object has got weight, it has got mass. Sorry, as long as an object has got mass, that particular object has got weight. Here. Here. It depends on this guy. The normal force. This normal force is equals to this. So friction is a function of the weight of an object. Apart from the weight of the object, friction also depends on what kind of surface a particular object has been put on. If you put some objects on a very smooth surface, then the friction is going to be less. But if you put it on a very rough surface, then the friction is going to be more. So there's always friction. There's no running away from friction. There is nothing like a frictionless surface. That doesn't exist. You can have a surface with very, very little friction, but there has to be friction. Are we clear? Are we clear?
Yes, sir.
Okay. The third situation which you can find ourselves with our box is that the velocity of the box is going to increase or the velocity of the box is going to reduce. So our box can move faster or our box can slow down. When this happens, if the box moves faster or the box slows down, we don't know what the reason why it's doing that, but as long as that happens, we can find the acceleration. Okay? We can find the acceleration. And this is where resultant force becomes very useful. We know we have an expression of resultant force, which is the F minus FF. That is the expression of resultant force. So we can use the resultant force to find the acceleration. Okay, so here, the resultant force, Fx, is equals to the mass multiplied by the acceleration along the x direction. What we are looking for in this case, if your resultant force is not equals to 0, the first two examples we've looked at, situations, the resultant force has been equals to 0. But if the resultant force is not equals to 0, how do you know that the resultant force is not equals to 0? It needs to cause the velocity of an object to change. Either increase the velocity or it needs to reduce the velocity. So if the velocity changes, then you know that there is a resultant force. So if there is a resultant force, and we know we have an expression of resultant force, which is F minus FF, we have F minus FF, that F minus FF equals to the mass of the object multiplied by the acceleration. So in this case, yes, we have found the resultant force, but what is more important is we have to find the acceleration. Because it's only when we know the acceleration of an object, that's when we can predict the movement of the object, where it's going to be, what's going to be its velocity at a particular point in time. So it's important that you find the acceleration here. So the acceleration, for us to get the acceleration, you just divide on both sides by m. So this side you divide by m, the other side you divide by m. If you do that, you end up with ax is equals to f minus ff divided by the mass. So you see a very, very wonderful application of the resultant force here. The resultant force of acceleration is equals to the resultant force F minus FF divided by the mass. So once you get the resultant force, then you divide the resultant force in a particular direction by the mass of that particular object, then it gives you the acceleration in that particular direction. With this acceleration, then you will be able to predict, if you know the initial velocity, using those equations of motion, v is equals to u plus at, s is equals to half u plus v in brackets multiplied by t, or s is equals to ut plus half at squared, or v squared is equals to u squared plus 2as. Using those equations, as long as you know the acceleration, then you will be able to predict where this particular object is going to be. What will be its velocity at a particular point, how much distance it would have covered, like that. So this is a very, very good application of a resultant force. You can use your resultant force to find the acceleration of an object by just dividing the resultant force by the mass of that particular object, as shown in equation 13. Are we clear? So in this case, it depends. If F, as you can see, if F is equals to FF, if these two are equal, if F, the pulling force, is equal to the friction force, then there will be no resultant force. Are we clear? So we start analyzing this expression. If F is equal to the pulling force, then the resultant force will not be there. You have no acceleration. So if you want acceleration to be there, F, it's either F must be greater than the friction force or F must be less than the friction force. Okay. If F is greater than... Sorry, you have a question? Yes, go ahead. Yes?
Question, sir. Question. A question, sir.
Yes, go ahead. We are waiting.
A question, sir.
I said go ahead.
Yes, sir. Now, sir, using the formula, it said F is equals to mx. Then when you find the deceleration which is negative, will that be considered as friction?
So
I'm
if...
saying if you find the negative acceleration on that formula given us,
Yeah, if you find a negative acceleration, then it means that the pulling force...
find the negative acceleration.
Yes, it means that the pulling
Consider
force...
friction.
It means that this pulling force is less than the friction force. So that negative acceleration is going to result in the velocity of your box slowing down. That's what negative acceleration does. Are we clear? So your box is going to slow down if F is less than the friction force. So a useful case is when the pulling force is greater than the friction force. In that case, the acceleration will come out to be positive and the velocity of the box will increase. Okay. However, you can also have a case like has been said, F is less than the friction force. So in that case, you end up having a negative acceleration. So basically, if you're having a negative acceleration, your box will come to a stop. The other interesting case is where there is actually no pulling force. You're not pulling this box. Yes? Is there a question? Okay. An interesting case is where the pulling force is equals to 0. So when the pulling force is equals to 0, there is no pulling force whatsoever. The only thing which is there is friction. Then in that case, we say that the box is sliding. When a box is sliding on a flat surface, the only force present along the x direction, the only force which is going to be present along the x direction, if your box is sliding, the only force which is going to be present, if this one is not there, then the sliding is going to be the friction force. So if F is equals to 0, so what you end up having is the following. You end up having minus, if this is equals to 0, you end up having minus friction force divided by m. This is going to result in an acceleration which is definitely negative. So when something is sliding, it will come to a stop because the acceleration is negative. It doesn't matter how long it will take, but it will come to a stop at some point. Are we clear? So this is how you find the acceleration when an object is sliding. Are there any questions? The slides are, oh, okay, fine. I think some internet thing cut. Let's do it. Okay, have they started showing? Okay. Are there any questions so far on the movement of a box on a flat horizontal surface? Whether that box is motionless, or that box is moving with constant velocity, or this box is moving with some acceleration, whether it is being pulled by a force which is greater than friction, meaning that this box velocity is going to increase, or whether this box is sliding to a stop. If the box is sliding to a stop, then there is nothing pulling the box. The only force which is present causing the acceleration is the friction. So in that case, your acceleration ax is going to be equals to minus the friction force divided by the mass. So this is how you find the acceleration. It's very important that you find acceleration. How much is acceleration? And the simplest way to find the acceleration is to identify which forces are acting along a particular direction. Then you add them, you obtain a resultant force. Then after you obtain the resultant force, you divide the resultant by the mass of that particular object using Newton's second law of motion, and that's what's going to give you the acceleration of the box. Then after that, once you have acceleration, then you can predict everything else you need to know about this particular box movement. Are we clear? Are we clear on this? Okay, looks like the slide stopped, connection lost.
No, sir, the network is got.
Yeah, I can see that. Yeah, my network is got lost. Okay. My network is connection is back. All right, just a minute. I'll share the slide. Again, it's gone. The next type of problem we tend to give you is that of a mass supported by a rope. You have a mass hanging or being supported by a rope. So as shown in figure 2. So when you look at figure 2 here, there are only clearly two types of forces which are present here. The mass has got weight. The weight of the mass is pointing down. Then this rope has got tension in it. The tension is pointing up. That's why the tension is pointing. So the tension is pointing up like that. So if we choose all the forces pointing in the positive y direction to be positive, so we're going to have a positive tension. Then if we choose this weight pointing in the negative y direction to be negative, then you're going to have a negative weight. Then after that, it depends on what we want, because right now the most important thing is for us to find the resultant. There's only two forces, and these forces are acting in the vertical direction, which is the y direction. So we cannot have a resultant along the x. There's no force acting along the x. The forces are acting only in the vertical direction. So in this case, the resultant force, our resultant force is going to be equals to, the resultant force along the y direction is going to be equals to, what did I do here? Okay, I also seem to have made a different choice here. And the choice is that if you cut, okay, if this thing was to get cut, if the rope was to tear and cut, this box would move down. Okay, so naturally, without the tension, the box tends to move down. So in that respect, I am choosing the direction in which the box would move naturally. If there was no tension stopping the box, I am choosing the direction in which the box would move to be the positive direction. So I'm choosing down to be positive and up to be negative. The reason why it makes sense to choose down to be positive is because the velocity of the box tends to increase as you go down. So as you go down, the velocity of the box will increase. If the velocity is increasing, it means that there is a net force, or there is a resultant force in that particular direction. So in the case of a mass hanging, being supported by a weight like by a rope like this, it makes sense that you actually choose down to be positive, then up can be negative, and that's what I have done. The result should not really change. It depends on what you have chosen to be positive and what you have chosen to be negative. So in my case, I've chosen the direction in which the box would normally move to be positive, and the opposite of that to be negative. So in this case, with the choice I've made, the weight becomes a positive force, so it's going to be plus FW, plus then the tension which is pointing up becomes a negative force, which is going to be minus Ft. So in that case, I end up having a resultant force which is equals to the weight minus Ft. So this is my expression of resultant force with the choices I've made, since I have taken into consideration that if there was no tension, then the box would fall to the ground. So it tends to move down. So that direction in which the box naturally wants to move, that's what I've chosen to be the positive direction. So we apply Newton's second law of motion, which is the sum of the resultant force is equals to the mass multiplied by the acceleration. So the resultant force in this case is this one, then the mass of the box and the acceleration, like that. So we end up having this. We end up having Fw minus t is equals to the mass of the box multiplied by the acceleration, which is 0. So now in this case, if we choose, if the box is not moving, if the rope can actually support the weight, okay, if the rope can actually support the weight so that the box doesn't move, if the box doesn't move, then it means that the acceleration is going to be equals to 0. That is, if the rope is strong enough that the box doesn't move. So the acceleration is going to be equals to 0. With an acceleration of 0, you multiply the mass times this acceleration of 0, you end up having 0. So you end up having the weight Fw minus Ft equals to 0. And this basically tells you that the tension in the rope is going to be equals to the weight. So this is what you have. So this is an interesting result which happens when your rope is strong enough that the tension in the rope is going to try to generate a tension which is equals to the weight, as long as the mass is not moving. So if you see a mass hanging from a rope, just know that the tension which is in the rope is equal to the weight of that particular object. Are we clear? As long as there is no acceleration happening, the tension which is in the rope is equal to the weight of that particular object. Is this clear?
Yes, sir.
Okay.
Yes, sir.
Okay, that's good. You can also have a situation where the mass is not motionless. Right now we've looked at the case where the mass is motionless. But you can also have a situation where someone decides to lower the mass. For example, if you're on a construction site, so you're a civil engineer, then you're building a high-rise building, okay? So if you lower the mass or you raise the mass at a constant velocity, if you lower the mass from up to going down, or you raise the mass from down going up at constant velocity, if you do that at constant, so that the mass is moving at constant velocity, it means that the acceleration along the y direction is equals to 0. Are we clear? It means that the acceleration is also equals to 0. So in this case, also, if you work out Newton's second law of motion, the sum of the forces is equal to the mass multiplied by the acceleration. So you're going to end up having the weight minus Ft equals to the mass multiplied by the acceleration, which is equals to 0. And you end up having a 0 this side. So you end up having Fw is equals to Ft. So this, you end up having the tension is equals to the weight also. So the tension is equals to the weight in two situations. One, when the mass is motionless. Two, when the mass is moving up or is moving down at constant velocity. So when the mass is moving up or is moving down at constant velocity, in that case, again, if you just look at a rope or a cable supporting a weight, like in the case of maybe some kind of elevator, okay, people are in an elevator, and that particular elevator, if you notice on an elevator, they will tell you this elevator can carry a maximum of 15 people, or they will tell you this elevator can carry a maximum of 10 people. The reason why they give you that maximum of 15 people, it's because the cables the elevator is attached to, they can only generate a maximum weight of that much. Probably after if you put more people, the cables are going to tear. If the cables tear, then your elevator is going to accelerate and it's going to crash to the ground. Okay, so that's what it is. The tension would depend on what the weight is. So you have with the same cable, depending on what weight is supporting that, depending on what mass you attach to this cable is going to generate, it will try to generate a force, a tension force, a tensile force, which is equal to the weight. But as you have seen, the tensile force is opposite the weight but equal. If it's opposite the direction of the weight but equal, that is basically an application of Newton's third law of motion. In Newton's third law of motion, we saw that if you've got two things interacting, there's going to be an equal and opposite force. And that's exactly what we have here. So in this case also, the tension in the rope is equal to the weight. So if the mass is not moving, but this mass is hanging on a rope, the weight of that mass is equal to the tension. The tension of the rope is equal to the mass. If the mass is moving up or down at constant velocity, again, in that situation, there is no acceleration. So that basically translates to meaning that the tension in that particular rope is going to be equal to the weight. However, you can also have a situation where a mass accelerates downwards with increasing speed. If there is acceleration, I'm sure you have heard of situations where an elevator dropped like a stone. Okay, if that happens, if the speed of an elevator starts to increase very fast, then in that case there is acceleration. When an acceleration like that happens, then what you end up having is the same expression of resultant force, which is the weight of the elevator minus the tensile force equals to the mass multiplied by the acceleration. Now that there's acceleration, you can work out what the acceleration is. So you divide the mass by the resultant force like this. So the resultant force is the weight minus the tension divided by the mass. When you do this, then you find your acceleration, AY. With this acceleration, you can predict what will be the velocity of this elevator or whatever thing is falling after a certain amount of time, and also you can predict what is the distance this particular thing has covered. Are we clear? The whole point here is you being able to work out what the acceleration is going to be. Apart from working out the acceleration, there are also a lot of situations where the acceleration is equal to 0. So you should also be able to identify under what circumstances is the acceleration equals to 0. If the acceleration is not equal to 0, then you need to find what the acceleration is. Are we clear? Any questions? We have come to the end of this bit. on how you work out resultant forces? You have to look at your objects, then you identify which forces are there. As you go through your tutorials, you learn to you get some practice on how which force is there and like that. Some forces live in cables or ropes, like the tensile force. Then if something is moving on a flat surface, there's definitely friction there. Then if an object has got mass, then there's definitely weight there. Then if this object is on a surface, then there's definitely a normal force there. So these are the actually what? Yeah, these are the types of forces you're interested in at this stage. You have a question?
I have a question, sir.
Yes.
Yes, sir. On the direction of forces in the x and y direction.
Mm-hmm.
I have a question like which signs do you consider when you're moving in the x direction and in the y direction?
Well, for me, I tend to consider the direction in which something is moving to be the x direction. If an object is moving in a particular direction, if it's moving to the left or it's moving to the right, then you choose that as your x direction. Are we clear? I tend to choose the direction in which a particular object is moving to be the x direction, like that. The other way you can do things is you can stick to the directions on the xy plane. Say, any force pointing in the positive x is going to be positive force. Any force pointing in the negative x is going to be negative force. If it's pointing up, it's positive. Pointing down, it's like that. Okay. So depending on what you have chosen, in that case, you have got no control. You have got no control on what the acceleration is going to be. It will come out as you have chosen. Okay, but it's much easier if you choose the direction in which something will tend to move. So you need to have an idea in which direction is this thing moving. If it's moving in this particular direction, then if you choose that as positive direction, then the opposite direction is going to be definitely become negative. That's basically my advice. It's easier. Choose the direction in which something is moving to be positive, then the opposite direction will be negative. Any force pointing in that particular direction will be a positive force. Any force pointing in the negative will be opposite the direction in which the object is moving will be treated as a negative force. Any other question? You have a choice here. When it comes to Newton's second law of motion, you as a student have a choice on how you choose direction. So I've given two options. Either you follow the xy plane, or you choose the direction in which the object is moving as a positive direction, meaning that the opposite of that will be negative. That's what I find easier and more consistent.
Sir,
Yes.
I have a question.
Yes.
What if you are dealing with two rods which are connected to a pulley?
Yes.
Then you discover that the other is heavier, it has bigger mass compared to the other. How do you go about that?
That is what is called a coupled system. The thing about the masses which are connected to each other is that they'll always have the same acceleration. Is that clear? If it doesn't matter how far I run, if I have a rope tied to me, then that same rope is also tied to you. It doesn't how fast I run will also determine how fast you run. Okay, so our acceleration is going to be the same. So for each mass, you work out the resultant force. You do the same things I've been doing for each mass. Okay. However, the acceleration, what you're supposed to be aware of is that the acceleration for these masses, because they're connected by a rope, will be the same. Are we clear?
Yes, I'm clear.
Yes. So if you've got two masses connected by a rope, by a cable, the acceleration will be the same, always. Because this rope, we are assuming this rope cannot be stretched like a rubber, like that. Since the rope can't be stretched, then the acceleration will have to be the same. So that's the one thing you do. So you work out the same thing you've done. So for example, if you had whatever problem we are looking at here, right? We had this mass, then this side there's a pulley, then over the pulley we connect this mass. So if figure 1 and 2 were connected by a rope. So 1, there's a rope, then it goes over a pulley, and I'm actually going to, I think, prepare a lesson on that like this. So in that case, you would work out whatever we have done here as we have done it, and also here as we have done it. So in that case, if there is because there is definitely going to be acceleration. So the acceleration you're going to find, as we have seen, in our case, our acceleration was where? This is acceleration. AX is equals to F minus FF divided by M. So this is the acceleration, because the mass on the top is going to slide on this particular thing, the horizontal flat surface. So there is going to be acceleration along the x direction. This is acceleration along the x, but this acceleration along the x direction is also going to be equal to the acceleration along the y direction. This one, AY. The reason is because they are connected by a rope. Since the acceleration is the same, then you can find out how much the tension is, because this thing has got tension in it. Then this other expression also has got tension in it. This other expression here has got a force. This force. So this force is what's going to be the tension. So we're going to look at, I think I'll prepare a lesson on a coupled system, a simple coupled system, so that you actually understand it. Say, if these things are connected by a rope, then the acceleration has to be the same. There's no choice about it. Are we clear?
Yes, sir.
Yeah.
But if the accelerations are the same, and the forces going to be different.
The forces are going to be the tension in it's the same rope. Okay? The tension will be the same. The tension acting on this box, since it's the same rope, acting on this mass, this side, when you connect it by a rope, the tension this side and the tension which is pulling on this thing are going to be the same. But the masses of the boxes can be different, or they can be the same. But the tension will be the same. So one, the acceleration is going to be the same. The acceleration of the other mass of the masses will be the same, and also the tension in the rope will be the same. Are we clear?
Yes, sir.
Okay. Yeah, that's what's called a coupled system. Yes.
I still don't get how they are going to have the same acceleration, because they're having different masses, meaning the mass, the force which is acting, the force of gravity which is acting.
They are connected by a rope.
So how are they going to
They are connected by a rope. It's like when you're pulling a car. When you have got a car which is dead, then it's being pulled by another car, a Land Rover which is moving. You think the acceleration is going to be different or what? Yeah, it's going to be the same. So how should it be different here? It's the same thing. Whether you're pulling it's the same thing you're doing. Are we clear? Yes. Okay, good. Any other question? So for a coupled system, you are going with the knowledge that one, the acceleration is the same, then two, the tension is also the same, because it is the same rope. Whether that rope passes through a pulley, the tension in the rope is going to be the same. Okay. The tension will be the same in the rope, but it will be pointing in different directions on the sides of the pulley. Usually the tension tends to point towards the pulley. That's what happens. Tension always points towards the pulley. So the tension in the rope or the table will point away from the box towards the pulley. The tension in the rope which is hanging, which is supporting the hanging mass, will point away from the mass, pointing towards the pulley. This tension will point away from the mass, pointing towards some pulley somewhere there, where this mass is, where the rope is passing. So the direction of the tension, yes, the direction of the tensions in the rope is not the same. However, the size of the tension is the same. Yes, go ahead.
So I have a question. How do you treat a situation where, let's say, 3 boxes are arranged in a crust on the surface of a table?
3 boxes are what?
To have pressed on the surface of the table in a cluster form. Then you intend to push those 3 boxes in a certain direction. How do you treat the masses if you want to calculate the surface tension?
I am not sure I understand what's going on. I'm not sure I understand what's going on. You put masses on top of each other or what?
Or you put them in a horizontal surface.
That's a flat surface.
Then you intend to push those 3 boxes in the same direction.
Okay.
You treat the masses to be the same or different.
You intend to push.
You want to calculate the... Yes.
You can treat them. No, usually masses are treated differently. Usually but in this case, there are a couple of assumptions you're making, because we don't know if these masses are with the same mass or they're with different masses, right?
Yes, sir.
Yes. So depending on the mass of the box, of the whatever mass it is, it means that that particular mass has got a different value of weight, right?
Yes, sir.
Depending on the weight, it means that there's a different value of friction. This, since they're moving, right? I'm assuming you want to move these boxes, right? So each mass is experiencing a friction value which is different. Okay? But since you've put them one after the other, you're pushing them in a particular direction, what I'm assuming is that the pushing force is the same. So for this same pushing force, which you are using to push, but the masses are, the friction forces are different. So you can isolate them. If you don't want to isolate them, you can probably, I don't know. Yeah, I think you can isolate them. Or you can look at them as one whole thing.
Okay.
Which might be easier. Because the other one is a bit more, you end up looking at 3 different equations. But again, in that particular case also, it's simple in that the acceleration is the same. Because you have got one thing after the other, so they are all moving at the same pace.
Yeah.
Yeah. So there are certain things you should be able to identify quickly, whether the acceleration is 0, or the acceleration is not equal to 0, or the acceleration is the same. Those things you should be able to identify them quickly. Once you identify that, then your life becomes much, much easier. Okay, we're going to stop here unless there's another question. Is there another question waiting? Okay, if there is no question, okay, we'll stop here. We'll meet on Thursday. We'll look at motion on an inclined surface. How is that different from motion on a flat surface? So we'll look at that. And probably that other on Friday, because the motion on an inclined surface I think we can finish in one lecture. And that other Friday we can look at motion of a coupled system. When a system is actually coupled, what happens? Okay, so see you on Thursday next week.
Have a blessed.
Thank you very much.
Good night, sir.
Good night.